Well, I may not be rich and famous and powerful like FDR, but I do have a fireplace. And also, I know how to do number 19 on this week's physics packet. So we're going to do that. This is Hey Duke. Hello, Hey Duke. Are you ignoring me? Hey, hello. He's clearly ignoring us. But here is the problem. Problem number 17. I've essentially just copied it from the packet. The two blocks of masses m and 2m shown in the diagram initially travel at the same speed v, but in opposite directions. They collide and stick together. How much kinetic energy is lost in this collision? So we like to start problems by listing the things that we know. But we don't really know anything in this problem. We know that we know the masses in terms of m. We know the velocities in terms of v, but we don't have any other real numbers to work with. We're just solving in those terms. So we don't really have a list to make. A couple of things I want to point out about this little drawing before we go on, though, is that, I messed up over here. I wrote magical frictional surface. I meant frictionless, and so instead of using whiteout, I just wrote non up there. See? I fixed it. Okay, the other thing, probably the more important thing here, is that you'll notice I put down negative v instead of just v. That's important because when we're talking about kinetic energy and momentum in this problem, we need to be treating velocity as the vector quantity that it is, not just the scalar speed. So I've added a negative there just to help clarify that so we don't forget it later. There's a note in the in that question that said only 7% of people got it right. A lot of people apparently missed it because of this issue. So we want to just take care of that right from the beginning. So first step, we need to find the momentum of the different parts of the system and the momentum of the system at the end so that we can use the conservation of momentum idea to find the final velocity. So if that doesn't make sense, just hang on. We'll do it step by step and it'll make sense in a minute. So the first thing I did was redraw this just so I'd know what I was looking at. Let's see. I'll go down about that far. So we know that momentum is mass times velocity. So the initial momentum of the little block is P equals N times V. The initial momentum of the bigger block is minus 2 mv. The negative from this vector quantity, the 2, because it's twice as big or as massive as the first block. So if we add these two pieces of momentum together, we're going to get the total momentum initially in this system. So I did that. Those two things add up to minus 1 mv. I accidentally put a squared there and I scribbled it out, so don't do that. It's minus 1 mv. Okay, so now we have the initial momentum of the system. Let's find the final momentum of the system. We know that this block is still m. This block still has mass 2m. We know that the thing is traveling backward at this point, or in a negative direction. We don't know its velocity, so I've put v sub f here to symbolize final velocity. You may have noticed that on the key for this, they used f with a little apostrophe next to it, or f prime. That's something that's used in physics sometimes to denote a final quantity. We haven't been using it that way, and I don't think you'll see it that way for the rest of this year, but be cognizant of the fact that sometimes that is used. So v prime or v apostrophe, we could use to say the same thing as v sub f or v final. So P equals m times v, right? So the final momentum is 3, because we have m and 2m. So 3m times v final. Okay, so that's an important thing for us to know. We can compare these since we know that momentum has to be the same before and after the collision. We can say that the initial momentum is the same as the final momentum. We can plug those two things in there, and we can solve for final velocity. So minus 1/3 of initial velocity is final velocity. And hopefully that makes a certain amount of just sort of instinctive sense to you that this whole mess, after the collision, the whole mess will be moving backward or in a negative direction because the bigger thing was moving in that direction. But it will be moving in that direction at a much smaller rate of speed or velocity because it was counteracted by this guy who was going the opposite direction when they collided. Okay, so this is the important thing that we have to carry forward into the next step. We're going to leave it there, but we're going to come back and get it in a little bit. Moving on, since we know both velocities now, we can find the initial kinetic energy and the final kinetic energy. Comparing them tells us how much kinetic energy we lost. So we can just do a kinetic energy problem for the initial conditions and the final conditions here. So let's do that. I resketched it again. Same thing, no changes here. And I figured out the kinetic energies of the two boxes before they collide. So here's the kinetic energy of box 1, 1/2 mv squared. Here's the kinetic energy of box 2, 1/2 2m negative v squared. If we add those together, we'll get the kinetic energy of the system initially, in other words, before impact. I have rewritten that in a slightly simplified way, and then here's our total. So initial kinetic energy is 3/2 mv initial squared. Okay, so let's figure out the kinetic energy of the system after the collision. I'll scoot my paper down. Here we go. Aha. Okay, so we're using minus 1/3 v sub I, or initial v, for this quantity because we need to go back to using the same quantities for v so we don't get confused. So instead of vf, we're using negative 1/3 vi. Here's m, here's 2m. So kinetic energy is 1/2 mv squared. So in this case, it's 1/2 times 3m, because that's our mass, times minus 1/3 v initial squared. We can simplify that down, and I didn't do that stepwise, but I know you guys can do it on your own. You didn't need me to hold your hand there. Kinetic energy final ends up being 1/6 mv sub I squared. Okay, so now we have kinetic energy initial, kinetic energy final, and by comparing these two things, we should be able to figure out what the difference is in the kinetic energy before and after the collision. Here's that right here. Kinetic energy final minus kinetic energy initial, amount of energy lost. Here it is, 3/2 mv sub I squared minus 1/6 mv sub I squared equals, and again, this had to go through a couple of convolutions to get converted into stuff that was easy to subtract, but you guys know how to do that, so I didn't do it step by step. The answer is 4/3 mv sub I squared.